Now it's time for our VBExtra, our next VBExtra. And today features Thomas Zurbuchen, and he's going to talk about the intersection of space science and exploration. And I have a multi-page, lots of things in it, bio for Dr. Zurbuchen. But I like to relate to my speakers a little bit, as you have noticed. Every once in a while I have an old story about them, but my oldest story about Thomas is about 2 or 3 months old. A couple of months ago, NASA had several industry days that they televised for some of the exploration programs, where they explained what they expected to do in the different lunar programs they're developing. And my memory of those, that in at least 2 of them, maybe there were 3, but at least I think in the PPE program and in the lunar lander program, and then maybe another one somewhere, they took pains to have the science folks come in and say, this is what we're going to get out of the program. Instead of being just the typical NASA, this is the hardware we're going to build and it's going to be great. It was this is what we're going to get out of it. And Dr. Zurbuchen was the one who came in and said those things, I believe. He's the NASA Associate Administrator for the Science Mission Directorate. He has his PhD and his master's in physics from the University of Bern in Switzerland. He's received a number of honors and 3 NASA Group Achievement Awards. Dr. Zurbuchen, please come and talk to us. Do you have charts?
Yeah, this is good.
That's it?
Thanks, sir. So it's a great honor for me to be here today. I hear there's not many scientists that are usually here. So let me tell you what science is. No, I'm just kidding. What I want to do is really talk to you about our excitement in exploration. And I want to tell you, start with kind of a personal way to talk about this, but also tell you where we are right now as part of the exploration campaign that we put together as an agency in response to the space policy directives that we have, but also then what our vision is going forward. We think what we're really about in science is we're explorers, just like human explorers, and we want to explore as one, in unison, because that's the best way to make progress. That's really what we're about. And it doesn't escape me that right in the front row here are NASA First members. That's a leadership program that it's very competitive. They got in there, and in fact, their project is all about Explore as One. So I'm going to steal your thunder, okay? Or borrow it. One of the things I told them is, credit is not a conserved quantity. Everybody can take 100% of credit. So for us, for science, in this anniversary year that we're looking at NASA, for us in science, this is the pivotal picture. It's a picture, of course, that talks about the trifecta of science. In the middle, the guy who barely can reach the rocket is Van Allen, who's a professor in the Midwest somewhere. Pickering, to your right there, is kind of at the nascent JPL. They're really the system engineer who put together the Caltech, in fact, the system engineer put together the instrument that, of course, Van Allen built together into a vehicle that was propelled by von Braun, who is over there at the right, the guy with the elastic arms, because he is taller than all the others, right? And so basically, what happened there is really that coming together of the propulsion side, which of course was developed not primarily because of these robotic instruments, but it was a transformative moment for all of us. This is January 31st, 1958, when that rocket took off, and it changed everything, how we look at nature and how we explore nature. Another moment that's just as important is this one, and of course it's an Apollo 11 moment, and it's frankly science hiding in plain sight. That chocolate paper there hanging from the little aluminum pole is an experiment. It's the simplest experiment that I'm aware of. Literally, it is aluminum, very expensive aluminum. And it's standing there. You see the shadow on the ground next to the astronaut. And of course, as the sun is hitting it, what's also hitting is the solar wind. The solar wind is, of course, the expanding atmosphere of the sun. It's so hot in a solar corona that it's not holding back its atmosphere. It's blowing it out supersonically. And with about 400 kilometers per second, these particles hit that surface of that aluminum foil and implant themselves. So many of these particles, they react when they get in there. You know, hydrogen interacts with aluminum or whatever material it is. There's some platinum in there too in that surface. Oxygen does the same. But the noble gases, they implant themselves and they just hang out like little bullets. And so what happened after that walk, the astronauts wrapped it all up, brought it home, and then what you do is you take that foil and put it in the lab and you heat it up. A little bit of temperature, of course, makes the surface stuff come off, and the more you crank up the temperature, all of a sudden those particles at just about a kilo electron volt, that 400 kilometers per second per mass unit, they're coming out like a peak. That was the best measurement of all of noble gases of the sun until 35 years later, where I finally beat the record by building a robotic instrument with a whole group and made measurements that had the same accuracy or better accuracy. That, by far, was one of the most productive experiments that related to the history of the solar system. And it was done right now, right then, by that astronaut standing there. That's what we mean when we talk about Explorers 1. It's that reaching across and locking our arms and doing things that otherwise we cannot do because both of us are there, science and human exploration. What happened later on the robotic side, this is in the late 80s, you see these missions, some of them, it's like, wow, are you kidding me? You know, we were already developing Hubble then, you know, in the late 80s. Hubble, of course, is in the news. It's just fine, you know. Chandra is back in science mode since yesterday. You know, so all these missions are in development. You see a lot of the bold-faced ones. Bold-face in this code is, you don't have to look at all of them, but you know, bold-face in this code is under development, whereas the regular fund are the ones that are already flying. And so you see, kind of look at the number, get a sense. This is where we are today, right? And so you see this tremendous movement forward of our understanding of the Earth. We're a better Earth today. We're a safer place today because of the work that these pioneers did and the missions that are flying right now, 20 in orbit right now, 19 under development at Earth. We learn about the world around us, whether it's the moon, whether it's Mars. Look at the kind of the tools that we deployed. They're getting ready for human exploration. We never think of Mars exploration independent of human exploration. We always think about what's there to come next, and then you look at the worlds beyond, where in any foreseeable future we're not going to be there, but we will eventually be out there in these other worlds. And of course the space weather missions of the type that I talked to you about, as well as astrophysics, that we're, of course, developing some of the most exciting missions, some of them being really hard, frankly, and we're struggling a little bit, whereas others are out there. One of them, of course, developed right here at Marshall-Ixby. So basically, for me, those are the missions that we're doing. See, just like before, I showed you Explorer 1, then I showed you the one together with human exploration. I want to show this picture, and this, of course, is the space station. Now, for me, to show that chart, I cannot, every time I show the chart, I think of a seminar that I ran at the University of Michigan. I ran the seminars. That's what the junior faculty does because they're not good at anything else, right? So I ran that seminar, and I invited this guy called Tom Donahue, was the chair of the Space Studies Board, and the title of his talk was How We as Science Failed to Kill Off Space Station. That was the title. And I'm like, wow, that's an exciting talk, you know. So he talked about it was a really depressing talk because he failed. Well, I'm so glad he did. Look at all the science that is hanging from the space station. There's a lot of science on the inside. I don't want to talk about that. You already heard others talk about this. That's often in the context of human exploration. There's a lot more attention giving to that. But let's look at the outside of this and the work that relates to the Earth's atmosphere, SAGE 3, for example. Lightning Mapper, which is hanging out there since this year, or also missions that are under development right now, both in astrophysics, in earth science, and also actually in heliophysics. NICER is one of them. NICER is kind of cool because it has two elements, and Jim Reuter is here. I just said hi to him. Hey, Jim. So kind of the one element of it, it's the most advanced experiment to look at a particular set of objects of neutron stars available. It takes really accurate clocks. Well, what it also is, it's a tech demo, and I call it for the Lord's GPS, right? Kind of these pulsars, they're out there and write time signals just as accurate as the GPS or more, are putting the time signals out. If we learn how to observe them, we can use that as a time standard, and that's what we demonstrated here. So that paper already came out in Nature, I believe, Jim, right? And I can tell you, I just, on the way here, I looked at the paper that we can't talk about yet because it's under embargo, but there's amazing science coming out on the science side, also in one of these journals. And so for me, that's why we do it. It's because we love the science and we understand that the uniqueness of the tool that is there, and we take advantage of it by doing this kind of mission. We could not afford this mission right now if it was not sitting on the space station. It is exactly the right platform for this type of experiment. So we're taking that forward as we now go and look at the moon as the next kind of high ground, as we extend our human presence into deep space, which is exactly what we should be doing. The moon, of course, is a destination I've always thought about. First of all, my dog is called Luna, so you see a little bit, from the team there. But the other thing also is I always thought, I told my kids, like, I just look forward, end of 1920, when we land again there with our industrial partners. I want to point to there and basically say, this is where we landed. Because you can actually see it. I built things for Mercury. You never see Mercury at night, because it's always on the other side of the dawn-dusk line, So I really look forward to that. Of course, we also there want to look at with humans and robotics together. That's the right way to do it. That's what we did on the space station. It's the right way to do it there. Also see it as a platform, as a series of platforms, and really take advantage of the fact that we actually can take more risks in robotics, because nothing on there has a pulse, right? So we really want to make sure that we kind of shake out these systems and kind of practice and go learn, perhaps taking more risks than we normally would, even for our space missions, because it's a strategic thrust that we want to go forward to. You, of course, have seen this, and I'm not going to talk about it, but in every case, we do one of those steps on the robotics side, whether we start with the ones already up there or the ones we're building right now. We think of them in the context of where we're going as a strategy moving forward. At the gateway, if we're doing the right thing, we're going to use the same way, these lessons that we learned at the space station, the same way for the gateway. Again, taking advantage of the unique orbit that it has, the unique platform that it is. By the way, I think that much of the science from the gateway will not be lunar science. Much of the science on the gateway will be in other disciplines. The heliophysics guys are much more excited immediately about this as an outpost for space weather measurement than any of the other disciplines, because it's absolutely clear. It can move around as it wants. Space weather hits you from whatever direction. And so for me, you can see that kind of activity. You already saw that the calls that we're putting out for missions of opportunity, we put the gateway in as one of the platforms now. And so we fully expect to use the same process that we use on a station for this infrastructure. And as we go think of that, yes, this is what Gert's slide looks like, which is we explore. I want to also add the word discover. For me, explore and discover relate to each other really deeply, but we want to develop. So in other words, our goal is not to always do the same thing. If in 20 years we do exactly the same thing within NASA that we did now, something went wrong. Our goal is to develop capability so we can buy, a capability that is out there from our industrial partners. Some companies that may not even be in existence yet, or some young companies, some of them won't make it. That's the name of the game. Some of them will. And our goal is, as we build that strategy, to also consider those stakeholders. Again, Explorers 1, not just focused on our human exploration programs, but also those stakeholders in these other worlds. Of course, we also think of Mars, kind of as we go forward, our goal, one of the goals, and beyond, of course, but our goals is to think of Mars, and as you know, we're closing in on Mars with the InSight lander. It's always a very nervous time. I always remind myself of the fact that as humanity, we have a 40% record of landing safely. The good news is that 40% that did land safely were landed by the team that's on our side, so I don't know how other people sleep. You know, so for me, Mars, you know, just like any other, like the lunar landscape, is just an amazing environment. It's worthy of exploration, and of course, we think right now of really building the first round trip back from Mars with samples, because that's the science priorities, but it's the first round trip because that's the first thing we need to do to actually think of bringing humans there and bringing them back. So we go in steps, thinking forward, leaning with robotics, following with human exploration, staying locked with our arms, taking advantage of when the human exploration platforms come out to really take advantage of what we're doing there. The systems, just like I talked to you on the first slide, that are being developed have transformative characters for us too. Systems both within the agency and on the outside. I tell you, the commercial cargo and eventually commercial crew here have really transformed science. The price has gone down for us to launch, and that's because of human exploration doing exactly the right thing. You know, so for me, I'm really excited to see this go forward, but also the rockets that are being developed by the industrial partners that are there. Of course, the mission that we have in mind is Clipper, which is out there at Europa. It's a world that keeps us all up at night just because we cannot barely imagine what is there. An ocean under ice in the worst radiation environment in the solar system, but with an environment, certainly as measured from Enceladus. We don't know that about Europa, but possibly with enough energy to actually have the major ingredients that are, we believe, are there at the transition of chemistry to biology, the beginning of life, and so many of our models, which may be entirely wrong, by the way, and we're good with that. So we want to explore together, explore with us. What are we thinking about right now? Think of Mars, just because I was right there. I could put the moon too. I think that part of human exploration on a surface in the future is actually not just an astronaut there. It's robots that are working together with that astronaut, charting a way ahead, of course, from orbit, but also from the ground. Robots that are there and can pick up, cart back, support the mission of the astronaut. That's a totally new way of thinking. We have not done that. The only place where that has really happened in detail is, of course, in the military. Well, I think that kind of work is important also here and will be increasingly important as we go forward. And really, the moment we set foot on these other worlds will be ever more important. But let's go beyond that. Think of that world I just talked to you about, Europa. For the next few decades, I'll take any bet. You know, in 40 years or 50 years, otherwise stick me up and tell me I was wrong. But, you know, we will not be there with humans anytime soon. But we want to explore with robots that are far beyond the capability that we have done. Landed robots that are exploring the environment, but also underwater robots that manage to get through the ice. The ice, by the way, being way thicker than is shown here, but can explore and communicate with each other, not because somebody on Earth is telling them what to do, because they have enough of the smarts to actually move things forward. That's one of the visions we have in front of us, in which robotic exploration can really be of tremendous value. Of course, that will come back, that autonomy, that will come back to the previous picture I just talked to you about on a landed surface and otherwise. And so for me, as we look back at the last 60 years, with this. This, of course, is the title page of our calendar this year, our kind of signal of pride, the eagle there with Explorer 1 in the middle, and the recognition that everything we're doing comes from that. We can only wait where we're going forward, Again, exploring as one together with human exploration. That's what we believe in, and I believe that many of you do the same. Thanks so much.
Okay, we do have a little bit of time for some Q&A. We've got microphones coming up both aisles. I see one right over here. Can you pass that down? Great, thank you.
Hi, my name is Jennifer Noble with the Aerospace Corporation. I just had a quick question. You talked about diverse platforms for scientific instruments and missions. How do you view CubeSats and smallsats being the future of science, and how is NASA investing in those and sort of bringing those to the forefront?
So I believe, thanks for the question. I believe that CubeSats and smallsats have an important part of the exploration of the future. And of course, I could show you how we could imagine the Earth exploration kind of the future with many observation points that are looking at the ground. We could imagine that these CubeSats, these small satellites, actually interact with us, provide data that are absolutely relevant to us in a way that only happens if we have enough of them. So for us, the small sats, the CubeSats, they're a tool that is the right solution for some of the problems we have. Not all of them. Some of them need to be big. It's just because of the nature of the science. But we believe that these small platforms are absolutely critical. That's why, frankly, the first strategic initiative that I affected in a direct fashion was that, to really grow that. What's just as important, by the way, is that we think of it in a different way than one of the big billion-dollar missions. We want to actually, I walk up and down on the hill on Capitol Hill and basically say, look, we're going to fail more with this, but I want to spend less. So it's an innovative tool, too, in which we move forward. I don't want to fail, ever. And any self-respecting scientist will put their entire life onto being sure that that mission doesn't fail. I know that. I lost a lot of sleep over my stuff. But the point is, I'm okay if we take a little bit of more risk than we normally do, and it's not going to work. So for me, the approach is to find the right tool. In each discipline, it's different. Earth science is really promising, so is heliophysics. There's some applications in the other areas. All of them are having programs right now. But at the same time, also recognize that the way we develop it also has to adjust. It's not a billion-dollar spacecraft.
Hi, so I'm Blair from the University of Maryland. So a lot of what we've been talking about throughout the past day has been sort of human spaceflight and what we're doing to work towards that. But I was curious what sort of things outside of Europa Clipper there are for long-term space plans for robotic missions to deep space.
How much time do you have? So, the answer that I would give you comes in three flavors. Relative to Earth science, our work is here to advance knowledge of the Earth as a system. And so the way we're going to do that, in accordance to the Academy's guidance that we base our prioritization on, is to actually make sure that we certain environmental parameters that are there and kind of talk about kind of the Earth as a system, that we continue doing those measurements, but we innovate in other parts. Some of them with small satellites, others with dedicated measurements that really go after questions we don't know yet. Sometimes we overestimate what we know about the Earth, or we overstate what we know about the Earth. There's many things we don't know about this Earth, and we want to be exploring them and utilizing them. For planetary sciences, of course, I talked to you about Mars sample return. We talked about Europa. Those happen to be the two highest priorities. There's a decadal that's going to kick off in a year or two, which will give us guidance. If I had, I guess, what we're going to talk about a lot with that is the outer planets. Remember, every picture that you've seen in your textbook, 95% of every picture that you've seen in your textbook on Uranus and Neptune are from that mission that started when I was a kid. You weren't born. So for me, for me, that's, I mean, so there's other questions there. In astrophysics, you know, there, of course, we're trying to get Webb off. Really hard mission to do, trust me. And if you don't believe, go get a tour from our friend at Northrop and look at it. If you don't understand the complexity by looking at it, let's chat. The other thing is, though, there's other missions that the Decadal just kicked off right now, and we're really interested to see what's coming there. Is it another kind of a exoplanet-focused one, or one that's more focused on the structure of the universe, you know, dark energy, and so forth. So I could go on for each one of those disciplines. The goal is our strategies, that science priorities are set by the academies, and we build programs around that. But really, our goal is to really find at any one time the science questions that is timely, and we can actually make a huge impact. If you want to start an astrophysics mission and you pitch that, the question I ask is, where's the potential Nobel Prize? Otherwise, I want nothing to do with it. With NASA, we leave that to the kind of fill in the edges. You know, of course, we do some smaller missions. We're targeted. Getting some new knowledge is just fine. But for a big flagship, we aim high because we owe that to our pioneers that are ahead of us. And the same is true with many of the other disciplines. Yeah.
Good afternoon. So my name is Alex from University of Illinois. So I have a question about the kind of the interhuman and robotic exploration you were talking about towards the end. So kind of based upon that, do you believe in like constructing like a system of basically either robotic that are like self-sustainable, like in a say like a even beyond like Europa exploration that can determine either making decisions or either choosing the objectives like based upon with like the advancing like the computation power we have will be like the future for like the exploration since the communication between say between a space center on Earth and then maybe the remote either rover or like even astronauts will be, the communication will be limited. Do you believe that will be like the, say the future, essentially launching like a space center into the space to complete like the exploration? Do you believe that that's going to be the future or?
Okay, now you have me stumped. This question has so many elements. I'm trying to figure out how to answer. Look, I mean, I think what's going to happen, I believe, is like if our human exploration, as our human exploration extends into deep space, and we commercialize low Earth orbit, what is happening is there's new modalities of science that are becoming accessible along the lines that you're talking about. So there are kind of using that thing as a lab in a much more accessible way, not by planning decades ahead, but by really using it just the way you would go to a lab somewhere else on Earth. Has promise of the type that you're talking about. You talk about kind of connecting the data sets across the various disciplines. I mean, I have to tell you, I believe that one of the frontiers that's harder to make slides of is one that's focused on just that question, you know, how we do that. I believe that the frontier of kind of deep learning, some people call it, artificial intelligence, others call it, is a frontier in which we really can learn new science in a way that we have not explored fully in most of the disciplines. I just give you a data point, and that is, if you look at the Hubble, we just talked about it, it's the most productive kind of science machine we have until something like last year or 2 years ago. Most of the papers were from new data. Like somebody measured something new and they wrote down a paper. Now, most of the papers are from all the data. Do you see what I'm saying? It's kind of pulling together the body of data that are there and basically looking at it as a whole. Of course, that's a totally different tool. So it's not some grad students finding the right picture and measuring things out and building a model and writing the paper. It's a computer with a log running hot in the basement, you know, and really addressing questions that are elusive to any single person or any group of people because of the fact that it takes the computational capability to look at all of them. Many of the questions that we're dealing with today with the structure of the universe, for example, and otherwise are of that nature. And so I believe what you're talking about, that computational network is a profound insight that I think we're spending a lot of time on.
All right. Well, thank you, Dr. Zurbuchen. Let's give him a big hand.
Thanks.